All right, so we're picking up. Last time I messed up a minus sign when doing the derivation for the potential energy of a dipole in an electric field, And it was a Bonnett calculus error. I was defining theta from the horizontal. So d theta is from the horizontal, so d theta is in that direction. The torque is in the opposite direction. So when I got rid of the dot product, a negative sign should have come out, which it did not before. So that minus sign basically cost me the minus sign in the end. Oh, apparently I just erased something too. Yep. And so the two minus signs would cancel out. You continue through it, the minus sign pops in again when we do the integral of sine theta, and we end up with potential energy formula, the negative P dot E plus a constant, because potential energy formulas always have a plus a constant, whether it's written or not. Now, the derivation method the book did was a little bit different. Philosophically, when you're trying to find the potential energy formula, you can do it this way, which is the way I've done it. Or you can look at it from the point of view of, if I have an external force and I want to move an object into place, how much non-conservative work do I need to do in order to put it in a position without changing the kinetic energy? Since non-conservative work is equal to the change in energy, and we're not changing kinetic, the non-conservative work would be equal to the potential energy. And so that's the approach the book takes. Any questions? All right, let's take a look at Gauss's law of electricity, where this, there's something missing here. Since we're talking about the electric flux through a closed surface for Gauss's law, there does need to be a circle to indicate we are talking about a closed surface. And I know it's a closed surface as opposed to a closed loop is because the differential is area, and so the area is closed. Later on we'll have the circle there, but we'll be doing along a line, and so that would just indicate that the line connects back up with itself. All right, let's apply it. We're going to solve some problems that we've done already using calculus and Coulomb's law. And in essence, Coulomb's law is in there. But if I have an infinite line of charge, uniform, linear charge density. So lambda is equal to dq dl. So no matter what chunk I take of this line, if I do the charge of that chunk divided by the length of that chunk, it's going to be equal to the same thing regardless of what I pick. So what I'm going to do is I'm going to put a Gaussian cylinder around it. So I've just got a line and I just have this pretend cylinder around it. And the cylinder has a radius of r and a length here of L, capital L. So applying Gauss's law, we do have a closed surface here. Again, it's not a real surface, it's a virtual surface, also known as a Gaussian surface. And I so know that the electric flux through this cylinder is going to be equal to the enclosed charge divided by epsilon sub naught. surfaces here. I've got a left end of the cylinder, right end of the cylinder, and then I've got the main barrel part. So this should be equal to the electric flux for the left side plus the electric flux through the right side plus the electric flux through the, what I'll call the barrel. From a symmetry argument, if I'm looking at the electric field at any point, that I know that I'll have some point over here with an electric field pointing in that direction, and then I'll have another one over here pointing the electric field in that direction. In other words, any horizontal, even though I've drawn it, any horizontal component is going to cancel out, because for any charge creating a horizontal component on one side, I'll have another one on the other side that will cancel out the horizontal component. So my net result is my electric field will be away from the line. So no matter where I am, electric field points away from the string or line of charge. All right. We're doing a dot product here between the area and the electric field. I know the electric field is going to be going away from the line. What is the direction of the area of this left side? The area vector on the left end of the cylinder. What is the direction of the area vector?
Towards the middle.
It is a closed cylinder. Which way?
That way.
That way, yeah. You said towards the middle, I assume you meant that way? PJ? Is that what, that's not what you meant?
I had like a circle equals towards the, like.
Oh,
you know,
as in towards,
yeah.
that-
I
okay.
had one of those moments, yeah.
okay. The area vector is perpendicular to the surface, and if the surface is closed, if it's a closed object, it points outwards. So my area vector here is pointing that way. Call it A sub L. What about the right side? What is the direction of the area vector on the right side?
So it would be the opposite direction.
Okay. So that's the area of the right side. My electric field anywhere on here is going to be perpendicular to it, because from the symmetry argument. So at this point right here, my electric field is that way. At this point right here, my electric field is that way. Over here, my electric field is that way. No matter where I am, I'm always pointing I'm pointing away from the line, whereas my area vectors are parallel to the line. Therefore, well, what is the dot product of perpendicular vectors? Dot product of perpendicular vectors.
0.
Yes. Dot products multiply parallel parts. So this is 0 and that is 0 because my electric field, no matter where I am on there, is perpendicular to the area vector. E dot A or E dot dA, either one. So the only thing contributing any flux is the barrel. And my electric field is perpendicular to the barrel no matter where I am. Since it's always pointing away from the line, my line is centered through the can. So this becomes, well, integral of E dot dA for the barrel. I know that the electric field and the area vector are parallel to each other, so this just becomes the integral of EdA. And since the electric field magnitude is the same regardless, because I'm the same distance away everywhere along the barrel, this is just EA. Gauss's law has now reduced to the electric field, and you can have something a little bit brighter, times area of the barrel, we'll put a little b there for barrel, is equal to the enclosed charge over epsilon sub naught. Well, what's the surface area of the barrel?
Would it be 2 pi RL?
So I have E times 2 pi RL is equal to my enclosed charge. Well, my enclosed charge is just going to be my linear charge density times L over epsilon sub naught. And now we can get rid of stuff. L cancels out, which is fortunate because L is just some arbitrary length that I made up. And we're left with the magnitude of my electric field. Just to differentiate from energy, magnitude of my electric field becomes lambda over 2 pi epsilon sub naught r, where r is the distance I am from the line. So if I put a charge into it, if I put a charge at distance r away from it, a point charge at distance r away, then the force on that charge, magnitude of the force on that charge, would be q lambda, or I'll make it a big Q lambda over 2 pi epsilon naught r. Actually, let me stick in the intermediate step. Would be the charge times the electric field, which is Q lambda over 2 pi epsilon naught r. And we can take it one step further to sort of connect it with what we did day one. I know that my electrostatic constant is equal to 1 over 4 pi epsilon sub 0. So therefore, 1 over 2 pi epsilon 0 is just 2 times that. So this is also 2 times the electrostatic constant, Q lambda over R, which I think is what we derived the first day, second day, at some point in the past. But obviously, a situation in which Gauss's law will at some point in calculus. Questions to hear?
Why did lambda substituting for the enclosed Q again?
That because it's a uniform charge density, that this ratio of charge to length is constant. And so if I'm looking at just the length here of the line that's within this cylinder, then that would have to be equal to the enclosed charge over L. So therefore the enclosed charge is lambda L. And the L canceled out.
Okay, thank you.
Yep. Questions? All right. Let's do another one that we went through and we did calculus to solve it, and let's do it faster. The infinite sheet of charge. So I have an infinite sheet at some distance r away. So infinite sheet with uniform is equal to dq dA. So what I'm gonna do is, again, I'm gonna use a Gaussian cylinder here and sort of keep it trapped like that. So I'm gonna have a cylinder that is, instead of being sort of along the line like we had last time, it's I guess the main axis of the cylinder is gonna be perpendicular to the infinite sheet. So I've got my cylinder here. I guess that's hidden on the other side. And then over here. We're going to go through the same process. I know from Gauss's law that the electric flux through a closed surface is equal to the enclosed charge over epsilon sub naught. So this would be the electric flux for the left side plus the electric flux for the right side plus the electric flux through the barrel is equal to the enclosed charge over epsilon sub 0. Now, by a similar argument that we made before, from a symmetry point of view, I know the electric field must be perpendicular to the sheet. The electric field has to be in those directions. So for the barrel, the area vector for the barrel is parallel to the sheet. The electric field is perpendicular, and so therefore, in this case, the electric flux through the barrel would have to be 0. Because everywhere along the barrel, the electric field is perpendicular to the area vector. However, not on the end caps. For this right end cap, what is the direction of the area vector? And so therefore, it's in the exact same direction as the electric field. And the electric field anywhere on this should be the same. There's no reason for it to be different at this spot than this spot. So this just becomes the electric field at some distance r times the area of the right side, A sub r. And over here, my electric field is going to the left, same as the area vector. So that's AE sub L, or the left side. Now let's see, we need a radius of this, so I'm going to make the radius of it capital R. My enclosed area here, similar to what we did before, so this would be Q over well, I want the charge enclosed by the can, so it would be that charge divided by this area right here. So Q enclosed would be that charge density times pi big R squared. So this becomes sigma pi big R squared over epsilon sub naught. This becomes the electric field times the area of the left cap, which is pi big R squared. And for the right, it's the same thing, so 2 of them. Pi R squareds cancel out, and we're left with the magnitude of my electric field is sigma over 2 epsilon sub 0, which is what we derived with calculus before. But I would contend you would not appreciate the simple way if we had not done it the hard way. And I'm looking at your faces and I can see the appreciation. Yep.
So the barrel is 0 because it's in the same direction as the,
So if I'm at this spot right here on the barrel, so just imagine I got a barrel here, pretend it's a cylinder. My area vector at this point is pointing up. And over here it's pointing towards you, there it's pointing down, here pointing towards me. It's perpendicular to this surface. The electric field everywhere along, anywhere, because of this sheet right here, that electric field is pointing that way. Or over here, that way. So my area vector is perpendicular to my area, my area vector is perpendicular to my electric field anywhere along this barrel. And so that's why it's 0. Is that sufficient?
yeah.
Other questions? All right, let's exploit Gauss again. I have a conductor, spherical conductor. Spherical conductor with empty cavity.